Welcome all. Myself Jissa David, Assistant Professor, Department of ECT, Rajagiri School of Engineering and Technology. This lecture I am going to discuss the topic Number System from the subject Logic Circuit Design under K2 syllabus. It includes need of number system, different types of number system and number system conversion. Let us start with what is the need of number system or what do you mean by number system. Number system which representing the information in the digital system. For an example, if you consider computer, it can understand only 0 and 1. But which carry some kind of information. So this is using binary number system. The digit value in the number system is calculated using the digit, the index where the digit is present in the number, base number, the total number of digits available in the number system. That means for an example, for a binary number system, it consists of only 2 digits, 0 and 1. So its base is 2. These are the different types of number system: binary number system, decimal number system, octal number system and hexadecimal number system. Let's start with decimal number system. The decimal numbers are used in our day-to-day life. It includes 10 digits, 0 to 9, so its base is 10. And here we are using a positional weighted system. So the weight of each position is expressed as a power of 10. For an example, if you consider the decimal number 2541, it consists of the digit 1 in the position, unit position, 4 in tens position, 5 in the 100 position and 2000 position. So its value can be written as like this: unit, 10, 100 and 1000. So or it can be written as with a weight of each position with a power of 10. So this value will become equal to 2541. The next one is the binary number system, and this is used in, for an example, in computers. And it consists of only 2 values, 0 and 1, and its digit it is called bit. And here the weight of each bit position is expressed as a power of 2. And here this is example for binary number system, and this 2 indicate its base, and here this 1 is called the least significant bit and this one is called most significant bit. This is the representation of an information in digital system. This is a signal with a voltage of 0 and 5 volt, and the 0 volt which is represented as 0 in binary and 5 volt it is represented as 1 in binary. So which this binary number which carry some kind of information. Now, what is octal number system? A group of 3 digits can be used to represent each octal digit, and it consists of 8 digits, 0 to 7, so its base is 8. And the weight of each position is expressed as power of 8. For an example, this is an octal number system and this 8 indicate its base number. And its values is always lies between the numbers 0 to 7. This is the representation of binary number and octal number. So group of 3 bits form an octal digit. And the last one, it is the hexadecimal number system. It is used in microprocessor and microcontrollers. And it consists of 16 digits. It includes 0 to 9 and the letters A to F. So its base is 16. And here the weight of each position is expressed as a power of 16. And this can be represented as like this. And the base, the 16 indicate its base. So these are the different types of number system. Next we will see different type of conversions. Depending on our application or our system, sometimes we need to be convert one number system to another number system. So these are the different types of conversions. Next we will see each conversion one by one. And let us start with the conversion binary to other number system. The first one is binary number system to decimal number system conversion. The process starts from multiplying the bits of binary number with its corresponding positional weights that will give a decimal number. For an example, this is a binary number. It includes integer part as well as a fractional part. So it can be represented in decimal number with multiplying its positional weight. So here you can see that each bit is multiplied with corresponding positional weight with the power of 2. And this is integer part and this is fractional part. So its positional weight here corresponds to 2 raised to minus 1, 2 raised to minus 2 and 2 raised to minus 3. And by computing this value, we will get corresponding decimal number, that is 22.125 in decimal. So this base indicate 10 decimal number system. So this is the process of converting binary number to decimal number. Next conversion is binary number to octal number. So in a binary number, 3 pair of bits is equal to 1 octal digit. There are only 2 steps to convert binary number into octal number. The first step is we have to pair 3 bits on both sides of binary point. And if there will be 1 or 2 bits left in pair of 3 bits pair, we have to be add zeros on extreme side. Second step, and we have to be write the octal digits corresponding to each pair. For an example, consider this is a binary value. We need to be convert this binary value into octal number value. For that, first make pair of 3 bits starting from this instant. Pair of 3. And here, the extreme side, there is a shortage of 1 0. Here there is a shortage of 2 0. And we are adding 0 on extreme side. Now you can see each pair include 3 bit. So we can write corresponding octal digit. So its octal number is given by, this is corresponds to 3, this is corresponds to 6, this is 5, this is 3, then 1, then 4. So this is the conversion of binary number to octal number. Then binary to hexadecimal conversion. It is almost same as that of octal number conversion. Here, a pair of 4 bits is equal to 1 hexadecimal digit. So again it includes 2 steps. The first step is make pair of 4 bits on both sides of the binary point. And if there will be 1 or 2 bits left in pair of 4 bits pair, we have to be add required number of zeros on extreme side. Then the second step, write the hexadecimal digit corresponding to each pair. Let's see an example. So we need to convert this binary number. And starting from this point, we are grouping it into 4 bits. Then we need to add zeros extreme point. Here we require additional 1 0. Here we require additional 3 zeros. Now each pair containing 4 bits, so it can be easily represented in hexadecimal form. And this is the corresponding hexadecimal. For binary 1010 is represented in hexadecimal, it is A. Similarly 1111 it is represented in hexadecimal, it is F. So by using this table we can write corresponding hexadecimal number. This indicate 7. This indicate 7. This indicate A. This indicate B. This indicate 3 and this indicate 8. So this is the conversion of binary to hexadecimal. The next number system, it is the decimal to other number system. So it includes certain process. So the decimal number can be integer or floating point integer. When the decimal number is a floating point integer, then convert both part of decimal number in the isolated form, or we have to be considered individually. It includes 2 steps. The first step is perform the division operation on integer and successive part with base r. List down all the remainders till the quotient is 0. Then find out the remainders in a reverse order for getting the integer part of the equivalent number of base r. In this, the least and most significant digits are denoted by first and the last remainder. Second step is the multiplication operation is done with base r of the fractional and successive fraction. The integer part are noted until the fractional part is 0 or when the required number of equivalent digits is obtained. For getting the fractional part of the equivalent number of base r, the normal sequence of integer part is considered. Let's see with an example. So we started with a decimal to binary conversion. Let's see this example 152.125. This is in decimal number. We need to convert this number to binary. So binary number system means its base is 2. So first we will consider its integer part, then we will consider its fractional part. Consider individually. So step 1, divide the number 152 integer part with the binary number base, that is 2. So this is the operation 152 by 2, that will give a quotient 76 with a remainder 0. And this is again divided by 2, again that will give remainder 0. And this quotient is again divided. This process is continue until the quotient is 0. So here we will get 2 by 2, 1, so the remainder will be 0. Again 1 by 2, the quotient will be 0 and there will be a remainder 1. So its binary number is represented by like this. Starting from this point, this is MSB, this is LSB. So this is corresponding binary representation of integer part. Similarly, for fractional part, perform the multiplication of 0.125 and successive fraction with a base 2. So here 0.125 multiplied with 2, because here for binary case its base is 2. Multiplying with 2, and that will give result like this. And we are considering its integer part. Here the integer part it is 0. So corresponding binary value is 0. Again this fractional value is multiplied with 2. Again that will give a value, and this integer part will give corresponding binary. Again it is multiplying. This process is continue until fractional part is 0 or required number of digits are obtained. And corresponding binary value is given by, this is the corresponding binary value, and starting from this point 0, 0, 1, so that its binary representation is given by binary point 0, 0, 1. So the binary of 152.125, it is given by considering these two. So this is the corresponding conversion from decimal to binary. Next is decimal to octal conversion. So octal conversion means its positional weight it is 8. So the decimal number, its integer part is divided with 8 and its fractional part is multiplied with 8. Let's start with an example, 152.622. This is in decimal number. So the first step is divide this number with 8. So when you divide, the quotient it is 19 and the remainder is 0. When you again divide this quotient with 8, that will give a remainder 3. Again we are dividing 2 by 8, so the quotient will become 0 and the remainder it is 2. So its by octal number is given by 230. This is the corresponding octal number. Now to obtain the octal number of fractional part, multiplying this fractional value with 8. Here we are multiplying it with 8. So that will give you this, and we are considering its integer part. Give the corresponding octal value. Again this fractional value is multiplied with 8. Again this is multiplying with, the processes continue until either the fractional value becomes 0, or here I am rounding the fractional value to 4 digits. So its octal value is obtained by 0.4763. Round to 4 digits. So if you want to round to 5 digit, you have to continue this process. So the final conversion it is given by decimal to octal. This is the value. Next, decimal to hexadecimal conversion. Considering the same example, so this is hexadecimal conversion. Same process, instead of dividing 2 or 8, here we have to divide the integer part with the 16 and fractional part multiplied with the 16. So dividing this number with the 16, we will get 98. Now for fractional we are multiplying, and here round to 4 digits. So here we will stop. So it is multiplying with a 16. We will get 9.952. Here 9 is the hexadecimal value. And its fractional value is again multiplying like that. And if this is 15 it is represented by F in hexadecimal. 11 it is represented by B in hexadecimal. So that its hexadecimal value is given by like this. The final, and it is down to 4 digit. Otherwise we have to be continue this process. And the final conversion it is given by decimal to hexadecimal 98.9F3B. Then next one is it is the octal to decimal conversion. The process starts from multiplying the digits of octal number with its corresponding positional weights. So let it be, we need to be convert this octal number to decimal number. So multiplying it with corresponding positional weights. So this is at position 0, 1, 2. So this is the integer part and this is the fractional part, and this value will give the corresponding decimal value. So this is the octal to decimal conversion. Next conversion it is octal to binary conversion. The process of converting octal to binary is the reverse process of binary to octal, and write the 3 bits binary code of each octal number digit. Example 152.25. We have to be write corresponding binary value with the 3 bits, so that 1 means 001, 5 101, 2 010, and here 2 010 and 5 it is 101. So this is the corresponding binary value of this octal number. Next, octal to hexadecimal conversion. It includes 3 steps. First, find the binary equivalent of given number. And second one is make the pair of 4 bits on both sides of the binary point. If there will be a 1, 2 or 3 bits left in pair of 4 bits pair, add required number of zeros on extreme side. And the third step, write the hexadecimal digits corresponding to each pair. Let's start with an example 152.25, which is in octal number. So first we need to be convert its binary value. So we are considering 3 bits of each digits. So this will be the corresponding binary equivalent number. Next we need to be group 4 bit as a pair starting from this instant. So this is the bits of a pair with 4 bits. Next step, we need to be write its hexadecimal value. This is 0, this is 6, this is 8, this is 5, this is 4. And this is the corresponding hexadecimal value. And next conversion is hexadecimal to decimal conversion. The process starts from multiplying the digits of hexadecimal number with its corresponding positional weights. For an example, starting with an hexadecimal number. This is the hexadecimal number. We need to be converted into decimal. So multiplying each digit with corresponding positional weights. Here A indicate its value corresponds to 10. If it is B, it indicate 11. If it is C, it indicate 12, like that. By calculating this value, we will get the decimal number like this. This is the hexadecimal to decimal conversion. Next one is hexadecimal to binary conversion. The process of converting hexadecimal to binary is the reverse process of binary to hexadecimal. Write the 4 bits binary code of each hexadecimal number digit. Let's see an example. Write down its binary digit with the 4 bits. 1 means 001, 5 means 010, 0101, 2 means 0010, A1010, like that. And this is the corresponding binary value. And this leftmost 0, no need to be considered. And this is the corresponding conversion from hexadecimal to binary. Then hexadecimal to octal conversion, it includes again 3 steps. Find binary equivalent of a given number. Then make the pair of 3 bits on both sides of the binary point. If there will be 1, 2 or 3 bits left in pair of 4 bits pair, add the required number of zeros on extreme side. Write the octal digit corresponding to each pair. So first we need to find the binary equivalent of a given number. This is its binary equivalent. Then here make it to 3 pairs. Here we need to add additional 2 bits. Here also we need to add additional 2 bits. Then write down corresponding octal value. And this is 1, this is 2, this is 4, 5, 2, 1, 1, 2. So this is the corresponding octal number. So these are the different types of conversion from one number system to other number system. Thank you.